Nigel, take it away.
So this is going to be fairly technical.
Good.
This morning.
We like that.
I'm assuming that's what you wanted.
Yes.
And I'm going to talk about some critical issues with respect to electrical installations on boats. And just to give you a little perspective on this, for years I used to survey the systems on the new boats of the Annapolis Boat Show for Sail magazine as part of their Best of Sail program. And I almost never found a boat. These are brand new boats straight from the manufacturer that was in compliance with the American Boat and Yacht Council standards, electrical standards, which govern the installation of electrical systems on recreational boats. So we continue to see a lot of appalling installations. And then, of course, the worst ones are generally ones that the owners have put in there. I see some pretty terrible stuff. So I'm going to talk about some of the core requirements when you're playing around with your electrical systems. And we'll start off by looking at the conductors that we put in the boat. And these need to be, you need to buy these from a marine chandler is the bottom line here. If you go to the local electrical supply place or to Home Depot or Lowe's, you're going to get cables with a solid copper conductor in them. And in boats, we need stranded conductors because of the flexing that takes place in the movement. If you take a solid copper conductor and just wiggle it up and down for a while, it'll snap because the copper work hardens. So we need stranded conductors. And ideally, we want all of the strands to be tinned because that enhances corrosion resistance. And fundamentally, if you buy conductors that are labeled UL 1426 or boat cable or BC5W2, all of those three things mean the same thing. That means the conductor has been built to an underwriter's laboratory standard called the UL 1426. You'll be getting a high quality conductor. The UL 1426 standard doesn't require tinning, but I've never seen boat cable that isn't tinned. So you'll get a conductor also with a high temperature insulation rating. So I'm going to move on to discuss what's the significance of this. When we put that conductor in the boat, we're looking at two issues in terms of how to size it. One is voltage drop. If you put a voltmeter across the terminals on a battery and measure the voltage, and then you turn on a load, a pump or whatever, it's got to be turned on for this to work. When you go to the load and you put the meter probes across the two terminals to the load, to the pump or whatever it is, and you compare the two voltages, you'll see there's a small difference. And that's called voltage drop. And it's because of minuscule levels of resistance in the conductors and the fuses and the switches and so on. And we allow that voltage drop in most of our circuits to be up to 10% of the voltage on the circuit. So if you have a 12-volt battery, and we'll say it's in a fairly well-charged state, so the voltage is actually 12.6 volts, and you go to the load, remember it's got to be turned on, you're allowed to drop 10% of that 12.6, so that'll be 1.26 volts in the wiring. So at the load, you'll see, I should have picked an easier number, 12.6 minus 1.26, whatever that comes to. So that's voltage drop. For one or two critical circuits, we want to keep that voltage drop below 3%. And to put this in perspective, to go from a 10% volt drop to a 3% volt drop, you actually have to quadruple the cross-sectional area of the copper in the conductor. I mean, so it's a huge increase in copper and in cost and in weight. So the boat builders all tend to build to a 10% standard because it's the most economical way to build a boat. But when you're doing your own wiring, you should consider going to a lower volt drop and even as low as 3% in some circumstances. And in a moment, I'll show you how to calculate this. So the other issue that we've got just before I get there is ampacity. That's the number of amps you can safely put through a conductor before it heats up, because that voltage drop that we've got in the conductor is generating a tiny bit of heat. And if the voltage drop gets high enough, or there's other resistance in the circuit, you can get hot enough to where you melt the insulation on the piece of copper that you've got in the circuit. So we also have to make sure that we don't ever get to a point where we melt down those conductors and start a fire on the boat. And when we're looking at ampacity rather than voltage drop, we're looking at the size of the piece of copper, the cross-sectional area, the temperature rating of the insulation around it. If you put a plastic with a low melting point around that bit of copper, you're going to put fewer amps through the copper before the plastic melts than if you have a high temperature melting point on the plastic. So for the same piece of copper, we can put more amps through the circuit without melting it down if we have a higher insulation temperature rating. And those that boat cable that I mentioned earlier has a temperature rating of 105 degrees centigrade, which is 221 Fahrenheit, I think. So then we take that piece of copper that we've wrapped the plastic around it, and we run it through the boat, and part of that conductor run goes through the engine room. And we're running the engine, and the engine room gets hot. So now we have preheated that conductor before we put any amps through it. So we have to derate the conductor, the allowable amperage that we can put through it, if we run it through a hot space in the boat. So we have a derating factor for high ambient temperatures. And then we have another derating factor. If we put that conductor in a bundle, and most of us have pretty large bundles on our boats, sometimes dozens of conductors. If we put it in a bundle, and one of those other conductors is running hard and it's warmed up, it's going to transmit heat to our conductor, and once again we have to derate it. So with that in mind, let's go to this website that Jan and I created, boathowto.com. And if you log into boathowto.com, you will find we have resources. This is on the free side of our paywall. We have paid for courses here, but on the free side of that paywall, if you go to resources and go down to tools and tables, and we go to the bottom of that page, you'll come to wire size calculators for boats. And if we click on that, we've got one for the ABYC, which is the US system, and we've got one for the ISO, which is the European system. So in the States, we have a counterintuitive method of sizing conductors. The bigger the number, the smaller the conductor. So like an 18 gauge conductor is really small. And then we go down to a 0 gauge conductor is fairly substantial. And then we run out of numbers because we've got to 0. So then we start stacking zeros. So we have 1 aught, 2 aught, 3 aught, 4 aught. 4 aught's the biggest we go to. Most of you will not have any conductors that size on your boats, but some of you will have 2 aught conductors, which are basically about the size of your thumb. In Europe, they have a much more logical system. They just tell you what the cross-sectional area of the conductor is in millimeters squared. So we'll use the American system since we're in the States. So if we go to the American wire size calculator, we've got 2 choices here. We've got wire size mode, and we've got ampacity mode. So let's start with the wire size mode. The first thing you have to do is measure the length of the conductor run from the source of power, which in most of our applications can be considered to be the panel in the navigation station, and then we measure that to the load and back. And when we measure that, we're measuring the actual length of the conductor, not the direct path, but however, if it's snaking around bulkheads and through bilges and so on, we measure the actual length and we double it for the return path. So we'll put in a conductor here, we'll say it's 60 feet long. And then we've got to find out what the load is.
Sorry, Nigel, would you share your screen?
Oh, I forgot to do that. I'm so sorry. Let me back up a couple of steps.
It's okay. Yeah, no, it's fine. I've been putting in the URLs into the chat room, but
right. I'm going to have to go back here. I'm really sorry about that.
It's fine.
And then I'm going to have to go to share screen. There we go. And then I'll go, where's the full screen function? I've just lost it now.
It's the little square in the next to the X in the top of the browser.
Right, I don't have that on this. Let me.
Okay.
Let's see if I've got it right here. Oh, you know what I'm going to do? I'm going to stop share again. I'm going to go back in here myself. I'm going to make that full screen right here. And then I'll go back to here and share. Okay, so I will back up a couple of steps. So if you go into our Boat How To website and you go to resources and you go to the bottom, you'll get tools and tables. And then if we go to the bottom of tools and tables, we get wire size calculators. And now we've got the ABYC one and the ISO one. So this is the using American wire gauge, and the other one is using millimeter squared. When we go into the ABYC one, we've got a choice of wire size mode or ampacity mode. So now we're going to enter the length of the circuit. I put 60 feet in here. It's a fairly long conductor one. Remember, this is in both directions. It's from the positive to the load and then back with the negative. And then we've got to put the load in. And to find that out, you'll have to look at the literature that comes with whatever it is you're powering up. And if you've got multiple devices on a circuit, then you need to add up all the loads, find out what the worst case load is. And then we're going to put the system voltage in. Most of you have 12 volts. I actually have 24 and 48 volts on my boat. So I have 3 different voltages. And then we're going to put the maximum voltage drop in. And in this case, we'll go for 10% because we're going for the minimum standard. And now we're going to put the conductor insulation temperature rating in here. I'm going to leave that at 60 C for the minute, which is the lowest rating you're likely to find on conductors, because some European boats use 60 C conductor. Mostly in the States, we never do. Now we've got the bundling factor. So let's say we're in a bundle here with 2 or 3 other conductors. So we may have to derate for that. And now we've got the ambient temperature issue. Is this going through an engine compartment? An engine compartment is basically a generic term for any hot area of the boat. And if any section of the conductor is going through a hot area, we're going to click that. And we're not in an AC circuit. And then down the bottom, it tells us the minimum size conductor we should use. And now look what we got. We got a little pop-up here that said you should use a cable with a temperature rating of at least 75 degrees centigrade. That's because we clicked the high ambient temperature, and the standards assume that the ambient temperature in an engine room is 50 C in the States or 60 C in Europe, which means we've preheated that conductor to the point at which we're not allowed to put any amps through it. So we're going to have to go back in here and raise the temperature on the insulation. We're going to have to get a higher quality conductor. And if we go to the next one up, 75 C, we discover we need a 12 gauge conductor. And this is determined by voltage drop requirements, which exceed those of ampacity. So what does that mean? When we do this analysis, we look at the conductor sizing from a voltage drop perspective, and then we look at the conductor sizing from an ampacity perspective. If we go ahead and put those 10 amps through this conductor, are we going to melt down the insulation? Whichever one of those requires us to put in the larger conductor drives the sizing process. And in this case, the table here is telling us that the voltage drop requirement is driving the process. Let's say I shorten that conductor run. I'm going to put it down, just for argument's sake, to 10 feet and see what happens. And then I go back down here. And now, look what's happened. I've reduced the length of the run, which means the voltage drop goes down because the voltage drop is cumulative over the length of the run. And we've got to a point now where the voltage drop is not driving the process, the ampacity is driving it. So we have to put a larger conductor in. And remember, in the US system, when the numbers go, we had what did we have before? I've already forgotten. I'll go back and put the 60 feet in there. I should pay more attention to what I'm doing, shouldn't I? We've got a 12 gauge conductor for voltage drop. So in this case, we've got a larger conductor because we've got that long conductor run, and voltage drop is driving the process. So when we reduce the length of the conductor run down to 10 feet, voltage drop no longer becomes an issue. And we discover that we can actually go to a smaller gauge conductor because of the short conductor run. So there's no great voltage drop issues. And we can get away with a smaller conductor. Let's go ahead and change this to 3% and see what happens. We're still at 14 gauge because we've changed the voltage drop requirement from 10% to 3%. But once again, ampacity is still driving this because it's such a short conductor run. And so the ampacity issue remains the same, and we need a 14 gauge conductor. And let me put this back to 60 feet. And we'll see what happens. Remember before, when we had a 60-foot run with a 10% volt drop, we needed a 12 gauge conductor. 3% volt drop, we've gone to 6 gauge.
Wow, that's amazing.
That's double the diameter. It's 4 times the cross-sectional area. It's very expensive to wire to 3%. So go and use these tables. Though I say so myself, this particular one that Jan developed for me is quite the most easiest and the best one in the marketplace. And again, it's free. So now we've got a separate table here. We've got the ampacity mode. Let's go and look at this. Let's say we already have in the boat some conductors. And incidentally, all of these conductors should have, their insulation should be labeled with the size of the conductor and the temperature rating of the insulation. If they're not labeled, then they're not standards compliant. Now, some European boats, they don't use labeled conductors, at which point when the boats are imported into the US, a sharp-eyed surveyor could look at that and could require the whole boat to be rewired because you have no idea without getting a micrometer out what the size of the conductor is. And even then you don't know what the temperature rating of the insulation is. So it's all got to be labeled. So let's say we've got some 16 gauge conductors on the boat. And we find that there's 75C insulation on them. And they're in a bundle of 2 to 3 conductors. So if we've just got a hot and a positive and a negative to a load, that's 2 current carrying conductors, in which case we've got to click the 2 to 3 bundling requirement. So we've got a duplex cable, positive and negative, and a common sheath. We click this. Let's say it's not in an engine room. We discover that the maximum number of amps we can put through this conductor is 10.5 amps. This ampacity is unrelated to length. Voltage drop is absolutely tied to length because the longer it is, the more the cumulative resistance. But ampacity is not, because as the conductor increases in length, the surface area increases proportionately. So you've got more heat dissipation capability. So it doesn't make any difference how long the conductor is. It's the number of amps you're putting through it that's going to determine whether it melts down or not how long it is. So in this case, we've got a 10.5 amp limit for this 16 gauge conductor that you found in your boat with a 75-degree temperature rating. Let's go ahead and bump this up, because most of the conductors, if you go to the chandlery, as I said, and buy your conductors, your temperature rating is going to be 105 C. Look what happens. We've gone to 17.5 amps on the ampacity. This is the same piece of copper. It's no bigger than the previous one. All we've done is to raise the melting point of the plastic that we've wrapped around that piece of copper. So now we can put more amps through that piece of copper before the conductor gets dangerously hot. That's from a standards perspective, you're allowed to go to the 17.5 amps from a practical point of view in your boats, you should never push the limits of these systems and go to the maximum you're allowed. And I would recommend when you're sizing conductors in your boat that you actually, even if you're using 105-degree insulation, that you use the 90-degree insulation column, because that will give you a bit of wiggle room. And in this case, it still stays at 17.5 amps. But if I were to change this, let's go into an engine room. We've gone to 14.3 amps. If I go to 105, we've got there's a small difference in the amperage that's allowed. So the reason for going to the 90-degree column, even with 105-degree conductors, is partly to be conservative, but partly because most of the devices that are in that circuit, the fuses, the switches, and so on, that we've put into that circuit, they're tested at 90 degrees, not 105. And when they get close to 90, they're relying on the conductor to take heat out of the device. And during testing, they're connected up to conductors that are helping to keep the temperature down. So if you go and stick a 105-degree conductor on there and you run it at 105 degrees, instead of absorbing heat from the fuses and so on, you're actually going to add heat to the system. And in the case of fuses, because they're thermal devices, you're likely to get nuisance blowing of the fuses. And you can also get meltdown boots on fuses and have all kinds of other problems. So at this point, do we want to take questions as we go along?
Yeah, if somebody has a question about wire sizing, the ampacity, and how to calculate it, specifically, you know, what I've learned right now is just that the temperature, the ambient temperature, what effect it actually has on these. But go ahead. Anybody's got a question? Raise your hand.
No, okay. So now what I want to do is, for some reason, I'm going to stop the share for a second and come back. I need to get back into here and go back to here. I want to access another part of our site, which is actually behind the paywall. So I have to log in. And what I want to do is talk about the terminals that we put on these conductors, because now I'm assuming that you've bought some quality conductors from the marine chandlery, and we're going to put some terminals on it. And I'm going to go back to share. All right. So the first thing we want is to get terminals that have a locking function. Ideally, there'll be ring terminals, because then if a screw comes loose, they're not going to fall off. However, ring terminals are a pain in the backside to install in tight spaces, because you've got to take the screw all the way out, put the terminal in, and then you go drop the screw in the bilges. So a couple of tools you might look for, which you can get from Lowe's and Home Depot. One is for screws that just have a slot in them, a slotted screw. It's called a split shank screwdriver. The tip of the screwdriver is actually split like this, and it's slightly tapered, and then there's a sleeve. So you stick it in the slot in the screw, and you pull the sleeve down, and it pushes these across, and then they tighten up inside the screw. So they hold the screw. And then for the Phillips screws, the ones with the crosshead, you can get a spring-loaded device that also grips the screws so that you don't drop them in the bilges. So those are really useful tools to have. If you use some fork-type terminals like this, then they should have a little tab on the end here, so that, again, if the screw comes loose, they don't fall off. We want our terminals to be tin-plated copper. If you go to the automotive store to buy your terminals, they're typically going to be tin-plated steel. When you screw down on them, you cut through the tin plating, and then in a marine environment, that starts to rust. So once again, we need to go to the chandlery for our terminals, and we're going to find they're expensive, but there's a reason for that. We want the barrels in here to be welded shut, so it's a closed barrel. Again, if you buy a cheap terminal, it's just two bits of metal that have been folded over like this. And when you crimp down on it, it can open up and make a lousy terminal. So we want the barrel to be welded shut. And then inside of the barrel, we want little serrations on here because that helps to grip the terminal when you crimp down on it. So there's a lot of features to a quality terminal that you will not get, including longer barrels. So you've got more of a contact surface area and you're less likely to screw up the crimping. And these kind of features you're not going to get if you go buying your terminals from Amazon. Not unless you look for quality terminals on Amazon. And then for the larger terminals, this is a 2-aught terminal. You can see here it says 2-aught. Ideally, we want a closed end to the terminal like this so it stops moisture wicking up into it. And then we need to crimp it. Now, I know most of you have a multi-purpose tool with a couple of little things for crimping on the end of it and a stripping tool and so on and so forth. You need to throw those cheap tools away and you need to buy separate strippers and crimpers so that we've got the right tools for the right job. And they're not expensive. You can't do decent work with cheap tools. So and when we put the terminal on, even a small conductor like this should be able to resist every amount of pull that you can put on it. So we'll look at how to do this right. First of all, you want some decent wire strippers. There's a whole variety of little strippers like this on the market. This one is nice because you can set the depth of the strip right here. This one you can set the depth of the strip with a little tool on here. These have a little screw on them where you can set the tension. So for very small wires, you don't just cut through the copper as well. So there's a whole range of these tools. When we get to big conductors, all too often people use a pocket knife. But with these stranded conductors, it's very easy to cut through some of the strands. So you want a stripper like this. It's got a little spring-loaded blade in here. You push the housing out around the conductor and then let go of it, and the spring pulls it back against it. And then you run this thing around in a circle like this, and then you pull it sideways, and you'll be able to just peel the insulation off. So we need the right stripping tools. We need to strip off enough conductor so that the bare terminal just goes through the bare conductor, rather, it just goes through the terminal and pokes out the other end a tiny little bit, but not enough to where it's going to interfere with the contact area on the terminal. So we're going to push it in, and we got a tiny little bit sticking out here. And then ideally, for most of our terminals, we want to buy ones with an insulating sleeve on them. Some of these sleeves are heat shrink, which we'll get to in a moment. You can shrink it down afterwards, but most of them are just plastic. And then you add heat shrink after the fact. And then we want the right crimping tools. And here, this is a brand new bow, by the way. Look at this crimp here. We can see for a start that it's way oversized for the terminal and for the conductor. And then whoever did it didn't have the right tools, so they just mashed it down with a pair of pliers or something. I bet you if I tugged on that, it would come straight out of them. So what we need is a ratcheting crimper. And they look like this. And most of them have 3 different sizes on them. One is for 18 to 20 gauge conductors, very small conductors, 16 to 14, and 10 to 12. So for 3 different conductor sizes. Typically these have 2 elliptical dies in them. The better quality ones, the dies are a different shape. The die that goes on the end of the terminal, close to where the conductor's sticking out, is more aggressive than the one that goes on the insulated barrel. So a lot of the cheaper ones, they're both the same size. So in which case it doesn't matter which way around you put the tool on the terminal. But with the better quality ones, typically speaking, the dotted side goes on the conductor side is running away from the terminal, and the other side goes on the terminal side. So you want to get yourself a nice ratcheting crimper, get some terminals, some conductors, and make a few crimps, and then tug on them as hard as you can. And you quite likely will find you can pull the conductor out of the terminal. So if you look on the side of these ratcheting crimpers, you'll discover there's a little wheel here with a tiny little screw. And if you take this screw out and turn the wheel and put it back into another one of these slots, you can either tighten or loosen the crimping action of the crimper. I've discovered over the years that most people don't realize that's there. So go ahead, do some practice crimps, pull them apart, tighten up the crimper. The arrow will show you which way is tighter. It says positive there and negative. And then try again until you know you're doing basically bulletproof crimps. And pull on those things as hard as you can. Years ago, Anchor, a company that makes high quality conductors and used to sell these tools, but the boat shows, they would have a bottle of whiskey behind the counter, and anybody that could pull a terminal off one of the conductors that they'd crimped got the bottle of whiskey, and they never had to give away a bottle of whiskey. The conductor should break before the terminal comes off. And then as they tug on it nice and hard, you're going to find with these really large conductors that very often they're very finely stranded. And for a given amount of copper cross-sectional area of the conductor, the more the strands, the fatter the conductor gets to be because of all the air spaces between the strands. So very often you'll find it's a real struggle to get the conductor into the terminal, but you need to make the effort and to try and minimize the number of strands that end up splayed out and don't end up going into the conductor. You want a decent tight fit in there, which brings me to another question. It's not standards. It doesn't break the rules to take two conductors and shove them into a larger terminal and then crimp on them. However, if you think about the logic of that, you've got a round hole, you're putting two round things into it. There's no way you can get a tight fit in there before you crimp on it. So it's an inherently weak way to make a connection. What we should do is just have a single terminal on a single conductor, and if we need more than one conductor to be terminated at the same point, then we need to put in a terminal post so that the individual terminals get bolted together, or a bus bar, which is a flat metal plate into which you screw bolts or screws, and you can put multiple terminals on the bus bar. When it comes to a terminal post, we're allowed up to 4 conductors, 4 terminals on one terminal post, but if we're going above 4, then we have to use a bus bar and put the multiple conductors on the bus bar.
One question, sorry to interrupt.
Yeah.
If you have those large terminals and your wire is a little smaller, is it possible to fill it with solder instead of crimping it?
Thank you for asking that. We do not use solder. It's not banned, it's discouraged. And the reason being, because when you solder a stranded conductor, you turn it into a solid conductor. And wherever that solder ends, it's a weak link in the system. And if there's any flexing, it's going to fracture right there. So what we do say, that solder cannot be the sole means of making a connection in a circuit, because maybe you solder 2 conductors together somewhere in a circuit. You then need some other means of supporting them to minimize any flexing that'll take place, which typically speaking would be a sleeve of heat shrink tubing. But by and large, we discourage the use of solder just because of the hard spots it creates. So no, the bottom line is you need to find the right size terminals for the conductor. And I know it's very tempting. I've done it myself to mismatch things because you don't happen to have the right one on hand. But we need to try and resist that. When we get to those large terminals, they won't fit in that crimping tool. And there are some cheap tools on the market like this one. It has different slots for different size terminals, and it's spring loaded. You put the terminal in there, the spring holes that cap down, and then you beat on it with a hammer until this bit touches this bit. And it'll make a surprisingly good contact. There are other similar devices that you hit with a hammer to make these, to put these terminals on. And here I've got one that I've just done with this piece of kit. And then I've cut through it with a hacksaw. And you can see how this is a multi-stranded conductor, but it's so well compressed, it looks like a solid piece of copper. So that they do a surprisingly good job. You can get tools like this for those large terminals. That's one that I have on my boat. You can get hydraulic crimpers, manual hydraulic crimpers for these large terminals, where you pump the handle in and out, and it makes a really good crimp. Or the real Cadillac of these things is a battery operated crimper with different size dies that you can put in there for different conductors and terminals. But these things with a set of dies are like $2,000. I mean, they're an outrageous price. I've never managed to find one on Craigslist or anywhere else that was affordable. Any terminal that might be subjected to water or moisture, or basically any positive terminal on the boat, should have heat shrink put around it. Heat shrink is a form of plastic which, when you add heat to it, it reduces in size, and as it reduces in size, it actually gets thicker. Heat shrink comes in all kinds of variations, mostly dependent on whether or not there's an adhesive lining in it, and we absolutely want the adhesive because it melts when you do the heating, and it comes out at either end and makes a watertight seal. And the other thing we want is a heat shrink ratio, the finished size as compared to the starting size, of at least 1 to 3. So if we've got a 3-inch diameter hole, for argument's sake, we'd end up with a 1-inch. But ideally, we'll go for a higher shrink ratio. You can get 4 to 1 ratio quite easily with adhesive lining. And this you can buy off of Amazon, and it works great. And so then you want the tool to heat it. You can heat it with anything. You can heat it with a cigarette lighter or whatever. But what you really want is a heat gun, which again you can get from Amazon or from or Lowe's or Home Depot for like $20. And you want a deflector shield on it like this, so that it sends the heat all the way around. And then you crank it up and you just move it slowly backwards and forwards, and you'll see this thing shrink down, and then you'll see the glue coming out the ends, and then you're done. And that way you'll have a really excellent connection on the boat that's likely to outlast the rest of the system on the boat. The final thing we should do is, when we connect these up to whatever it is we're connecting to, a bus bar, a terminal post, a piece of kit, if there's any likelihood whatsoever that we get any kind of moisture or condensation on the conductor, we want to put in a drip loop ahead of the connection, a little bit of surplus wire like this that comes down, and then we make the connection. And that way, if any moisture ever wicks down the conductor, it'll drip off before it gets to the connection, because those connections are the weak link in our system. And yes, go ahead.
We have a couple of questions in the chat room.
Yep.
The first one is, what are your thoughts on using silicone grease on conductor wires prior to inserting them into the terminal to help with connectivity and corrosion resistance?
So, you know, my first boat that I wired 1978, so we're talking 40 years ago. I've never used any of these greases, so dielectric, conductive, whatever, on my circuits. And that boat, which has been cruised for years, ever since we built it, the electrical circuits are still fine. I don't think you need this stuff if you make the connections properly with the right tools, and then you put the heat shrink on there. It's not going to do any harm, but I don't see the need for it. In the same way, if you put the drip loops in there and just make sure that you don't install pieces of kit where they're going to get wet or submerged, then you don't really need the additional corrosion inhibitors on the terminals. They're not going to do any harm, but I've actually never used them. I've got them on my boat, but to this day, I don't think I've ever made up a terminal where I've actually used any of these corrosion inhibitors. There was another question.
Does anybody else have any questions with regards to conductors, heat shrinking, crimping, and soldering things? You just gave me a big job. All right, thank you. Let's move on.
So I'm going to actually not follow the order of your agenda there, Dieter. I want to get to overcurrent protection.
Yep, fine.
These are fuses and circuit breakers, because now we've made up our conductors. We've done a really good job. we need to make sure that if we do accidentally overload them, they don't set the boat on fire. And the way we do this is with fuses and circuit breakers. So people tend to think that a fuse or a circuit breaker is in the circuit to protect the equipment in the circuit. It's got nothing to do with equipment protection. The sole purpose of the fuses and circuit breakers on our boats to make sure that if we get an overcurrent situation where we've exceeded the ampacity, the amp rating of the conductor, and now the conductor is getting hot enough to melt its insulation, the sole purpose of that fuse and circuit breaker is to shut the circuit down before we get there. So the corollary to that is that the fuse or circuit breaker has to be at the front end of the circuit. It has to be close to the source of power, which in our case is the battery, because the battery is the piece of kit that has the ability to create a huge number of amps down that conductor. So the fuse has to be at the battery end of the circuit or the circuit breaker. And I've forgotten all the other things I was about to say. So, and that fuse or circuit breaker, the maximum amp rating it can have is based upon the ampacity of the conductor. So we go all the way back to that ampacity table that we have in our boat how-to site that you can access for free. You go to the ampacity side of it. You put in there the conductor size. You put in there the insulation temperature rating. You put in there whether or not it's in a hot ambient environment. You put in there if it's bundled. And then it'll tell you what the maximum number of amps are that you can put through that particular conductor. That tells you the maximum amp rating you can have for a fuse or circuit breaker. Now, we do have a little wiggle room in the standards, because that is likely to come up with a number for which there is no exact match with a fuse or circuit breaker. Let's say it comes up with, I think in one of those examples I had earlier, it came up with like 10.9 amps. Well, you're not going to find a 10.9 amp fuse. So the standards say you can go, the fuse or circuit breaker has to be as close as practicable, but up to 150%. So that 10.9 amp ampacity rating for that conductor. So a lot of people look at that and say, oh, 150%, that's 15 amps. And they'll go stick a 15 amp fuse or circuit breaker in the circuit. It doesn't say that. It says it's got to be as close as practicable and not to exceed 150 amps. So this particularly occurs when we get to high current circuits. Those 2-aught conductors that we have on our boats, if they're 105-degree insulation and they're not in a hot ambient and they're not bundled, they're rated at 330 amps. Well, you won't be able to find a 330 amp fuse or circuit breaker. So people would look at that and say, well, 150% of 330 is 480 amps, and they'll go put a 450 amp fuse or circuit breaker on there. That's not allowable. You can easily find a 350 amp fuse or circuit breaker, so that's as close as practicable. So there's no point pushing the limits of these systems, because if you do get some kind of a short circuit on the boat, you're going to pay a heavy price for it, because the fuse or circuit breaker may not protect you and you may burn up the boat. So that's how we size the fuses and circuit breakers. As I mentioned, they go at the front end of the circuit, so they need to be close to the source of power. So how close? Well, the generic rule is that the fuse or circuit breaker has to be within 7 inches of the source of power. If you're looking at a panel where you've got an incoming feeder conductor from the battery, and then you've got all these circuit breakers attached to a bus bar in the panel, and then you've got conductors coming out of the circuit breakers. Those circuit breakers are actually physically attached to the bus bar, so it's 0 inches, because they're protecting the circuits downstream of them. But if it's not that kind of a situation, then the generic rule is 7 inches. At the battery, you can get fuses that bolt to a battery post. So then once again, it's 0 inches. We call them MRBF fuses. There are a number of reasons we can't use those in some of our installations, which I'll get to in a moment. I better make a note to myself so I don't forget. So let's assume we haven't used that. So it's really hard to put a fuse within 72 inches of the battery because we're running big conductors off the top of the battery because we're running the whole boat. So the standard says we can, the fuse or circuit breaker, and it's going to be a fuse, must be as close as practicable, again, and not to exceed 72 inches. So you can go up to 6 feet, but that doesn't mean you can automatically go to 6 feet because we've got that as close as practicable piece in there again. So at the battery, we can go up to 72 inches, but we need to be as close as we can get it. And then the standard has in there, up to that first fuse, which is the main fuse in the system, there has to be additional sheathing on the positive conductor. So we know that we need another layer of protection because there is no overcurrent protection until we get to that first fuse or circuit breaker. So the easiest way to put that additional protection on is to take the split loom, that plastic stuff with a slit down the side of it, and then you can just pop it over there to give you that additional protection. When we get beyond the battery, we're going to get to a battery switch in almost all of our installations. And at the battery switch, we're actually allowed to go up to 40 inches. But again, it says as close as practicable and not to exceed 40 inches. And then we have to have the additional sheathing in the conductor up to that fuse. So let's say that we come off the battery with a 2-volt conductor. That's one about this size. We put in our first fuse, that's our main fuse. Then we go to a battery switch. And then we come off the battery switch up to our panel, distribution panel. And in this case, we come off the battery switch with another 2-volt conductor and we go up to the panel. So we've got 2-volt from the battery to the switch and 2-volt from the switch to the panel. We do not need an additional fuse at the switch because that conductor coming off the switch has the same ampacity as the one coming onto it. And therefore the fuse that's protecting the conductor coming to the switch will also protect the conductor coming off the switch. So when we have to add additional overcurrent protection is when we step down in size with the conductors. So let's say we had a 2-volt conductor to the switch, and then we come off it with a 1-volt conductor. So now we remember when the numbers go in that direction, the conductors get smaller. So we've gone from a larger conductor to a smaller conductor. Anytime we step down in conductor size, then we need additional overcurrent protection. And that's where the 7-inch rule kicks in, or the 40-inch rule if we're coming off the main battery switch.
Question on that.
Yes.
That's on taking the energy out of the system.
Yeah.
What are the requirements on the charging side of the system? So, you know, your solar chargers, your MPPTs,
right. So
and all
excellent question. So the way the standards are written, it says we need overcurrent protection at or close to any source of power. So what are our sources of power? Alternators, solar panels, battery chargers, inverter chargers, and when they're in charge mode, maybe fuel cells on some boats. However, there is in the standard, this is actually something I got put in there, if the maximum possible output of the charging device, let's say it is a solar panel, is below the ampacity of the conductor. Let's say we put a 10-gauge conductor on there, which has got an ampacity, I can't remember off the top of my head, but maybe 50 amps. The solar panel is never, if it's never going to be able to put out 50 amps, it's never going to melt down the conductor, then we don't need the overcurrent protection at the solar panel. Now, battery chargers will have it internally. They all come with overcurrent protection. Inverter chargers will have it internally. So now many of us put on high output alternators on our engines. So on my boat, I've had, right now I have a alternator that I run it at 48 volts. If it was 12 volts, it's capable of putting out 700 amps. But in any case, we have these big alternators. Let's say we've got the APS, the American Power Systems, has a 12-volt alternator that will put out 360 amps. And we put a 2-volt conductor on that, which is the largest we can physically find we can hook up in reasonable manner, that 2-aught conductor outside of engine rooms has an ampacity of 330 amps. But now it's in an engine room, which we know it's going to be hot when the alternator is running because the engine has to be running. And we may strap it up with the negative conductor. So now it's bundled. We've got a bundle of 2 to 3. We discover that we have to derate that 2-aught conductor down to maybe 280 amps. And we've got an alternator that can put out 360 amps. Theoretically, we're supposed to have another overcurrent protection device there because the ampacity of the conductor is below the maximum output of the alternator. The problem being, if we put a fuse in that circuit close to the alternator, the heat generated by the alternator and the engine will also preheat the fuse, and it will blow prematurely. And when the fuse blows, we'll destroy the alternator. So in practice, we don't put the fuse there, but every time we do that with these super high output alternators, we're actually pushing the limits of the standards and of what we should be doing on our boats. So there are gray areas where we start to run into a little bit of a trouble with some of these requirements. So then with fuses, they have different tripping and blowing rates. I think I actually have a couple of slides on the same with circuit breakers. This is a fuse. So typically speaking, in a standard ambient temperature, which is like 77 degrees Fahrenheit, the fuse or circuit breaker will actually not blow or trip until 130% of its current rating. So if it's a 100 amp fuse in 77 degrees Fahrenheit, it's not going to blow until you put 130 amps through it. So there's a fair amount of margin built in there. But as the ambient temperature goes up, you get rid of that threshold. And the other thing that happens is, as the current goes up, let's say it goes to 300 amps, so we've got a sudden huge surge through the system, the fuse is going to blow quite quickly. And if we go to 1,000 amps, it's going to blow almost instantaneously. So we have this curve of time versus amps to see how quickly it will blow. So on most of our boat circuits, we want what's called a slow blow fuse, which has a fairly slow curve to it, so that if we get sudden spikes through the system, it's not going to nuisance blow. There are some devices like sensitive electronics. If we're going to protect them with a fuse at the device, we want a fast blow fuse that's going to blow the moment it sees anything over the rated amperage of the fuse. But typically speaking, we want fairly slow blow fuses and circuit breakers. The only circuit on the boat, there are the 2 circuits on the boat where we're not required to put overcurrent protection. One is a temperature sensor. So if you strap a temperature sensor to your battery post, it doesn't need overcurrent protection. And the other one is a cranking circuit. And the reason we don't put it in cranking circuits is because typically speaking, if you looked at the voltage drop on the cranking cable, you would find it's over 10%, because starter motors are very tolerant of voltage drop. We're not worried about the conductor heating up, even if the ampacity of the conductor is below the amp draw of the starter motor, because we're only running the starter motor for a second or 2. Worst case, 10 or 15 seconds. So the conductor, even though if it's undersized, is never going to get hot enough to melt down. So if we stick a fuse in that circuit based on the ampacity of the conductor, every time we crank in cold weather, we're going to blow the fuse. So the standards don't require a fuse in that circuit. However, if we get a short circuit in the starter motor, we're going to start a fire. And we've had a number of fires on boats because of that. So I always put a fuse in that circuit. Because we're not required to have a fuse, we don't have to base the fuse on the ampacity of the conductor. We can basically put in whatever we want. So for a typical like 100 horsepower sailboat auxiliary engine, I'll put a 300 amp slow blow fuse in that circuit. And it's never going to blow under cranking currents. But in the event that we get a short circuit in the starter motor or in that circuit, the fuse will blow and protect the boat. So I do actually always fuse those circuits. So now I want to come to something called the ampere interrupting capability of a fuse or circuit breaker. If you take a battery, even a relatively small one, a group 27 battery like this, and you drop a wrench across the battery post, it'll melt the wrench instantaneously. I mean, there'll be a huge spark and it'll just melt the end off the wrench. The reason it'll do that is if you put a dead short, it's called a voltage short, across even a small battery, you can have 1,000 amps going through that circuit. Batteries can produce an awful lot of energy. You take a bigger battery, you take like a Group 24 AGM battery, one that's physically about this size, rated at 200 plus amp hours. You put a voltage short across that, it can deliver 3, 4, 5,000 amps for not a very long period of time, but you can get huge amps out of it. You take a lithium-ion battery. I was just looking at some statistics yesterday for a voltage short on a lithium-ion battery. It was 13,000 amps. And we're fairly certain that some of these bigger lithium-ion installations, it could be 15, 20,000 amps. So a fuse has a rating for the maximum number of amps it can safely interrupt in that dead short circuit. Because what happens is they'll arc over, and then even though the fuse is blown, you've still got a circuit, and the fuse is not doing anything. So that maximum number of amps that it can safely interrupt, that's the AIC rating. The first fuse, the main fuse coming from batteries, if we have a relatively small lead acid battery bank, needs to have an AIC rating of 5,000 amps. In practice, what we want on those circuits are A&L fuses, which come in a holder that's about this big. They're not terribly expensive, and they have an AIC rating of 6,000 amps. So they're good for pretty much any lead acid battery bank up to a pretty decent size. So just stick an A&L fuse on there, and I don't know, maybe $20. When we get to larger battery banks, we need something with a higher AIC rating. And in practice, in terms of what's available in the marketplace, which is affordable and not too big and clutchy, the next step up is a Class T fuse, which comes in a fuse holder about this size. And they're typically maybe about $80. And a Class T fuse has an AIC rating of at least 20,000 amps. So for those larger installations, and for any significant lithium-ion installation, you need a Class T fuse in the circuit so that you've got that very high AIC rating.
So for example, for 1,000 amp hour bank at 12 volts, what kind of a Class T fuse would you suggest?
So then the fuse itself, the amp rating of it, is going to be dependent on the size of the conductor that comes off that battery. If it's like a 2-aught conductor and it's not bundled or anything, it could be as high as 330 amps. If it's a 4-aught conductor, it could be 400 and something amps. So the actual amp rating is determined by the conductor. The AIC rating is just given by the fact that it's a Class T fuse. So all those Class T fuses, irrespective of what amperage they have an AIC rating of at least 20,000 amps in that situation. I was on a boat one time. We had a really large lithium-ion battery bank, and the boat owner had wired it up for 144 volts, and he'd wired it to an electric motor that he got out of a drag racing car. They have electric drag racing cars now, and he'd stuck it on a jet drive. And he'd never fired it up. I went over there to see this demonstration. We're in a high-end marina in San Diego. And I said to him, Jack, what happens when you turn this thing on? How are you going to control it? He said, we've calculated that the load of the jet drive is going to keep the electric motor down to such and such, and that effectively will control the power we get out of the whole system. And I said, I don't think it works like that. I think if you kind of strangle that electric motor, it was a 1,500 horsepower electric motor, it's going to look like a dead short to the system. And he said, what happens then? He said, well, we have a fire axe. Well, I thought he was joking, but they did. They had a fire axe, and they had the main conductors laid out on 2x4s and had the axe ready to chop the conductors. So they had a relay that's a switch you can operate remotely, a 400 amp relay. And we're on the transom looking down into the engine room, and he flicked the relay on and off, literally as quickly as that. And in that fraction of a second that the relay was on, that the remote was activated and the relay was closed, the relay arced over because it didn't have a high enough AIC rating. And we got a plasma arc across the relay. We've got a 20-foot rooster tail coming out the back of the boat. We're both looking at the dock and wondering where we're going when the cleats come loose. And in the meantime, we've got little bits of molten copper splattering all over the engine room and lots of little fires going on in the engine room. And they hadn't sharpened the fire axe. So the guy is hacking away at the cables, and it took him a little bit of time to cut the cables. And then we put the fires out, and everything was actually okay. But the bottom line there is that they didn't have a high enough AIC rating for the potential short circuit currents in the system. And you need to make sure, especially those of you that have large battery banks, that you've got either an AML fuse with the lead acid batteries, or preferably if it's a big lead acid bank, any lithium ion bank, that you've got a class T fuse in the circuit so that you've got that high AIC rating. All of these fuse holders have stainless steel bolts and nuts and washers. Stainless steel has less than 10% conductivity of copper. So if when we put these fuses in, we bolt down and we accidentally get a stainless steel washer between the fuse and the conductor terminal. So now this fuse holder was laying flat in the bottom of the boat. We loosened the nuts. These ANL fuses have a slot on one end, and you push it in like that, and then a slot in the other direction this way, and you push it in and slide it in, and then you tighten the nuts. Well, we didn't notice that one of the washers had dropped down, and now instead of being on top of the fuse, it's underneath it. So it's now between the conductor terminal and the fuse. That washer is going to act like a little heater, quite a big heater. If we start running high amps through that conductor on a continuous basis, which we will be doing if we've got a high output alternator charging a discharged lithium ion battery bank or even a discharged large lead acid bank, we start running high amps through that circuit on a continuous basis, that single stainless steel washer can get hot enough to start a fire. What it may also do is generate enough heat to melt the fuse, even though we don't have an overcurrent situation. And when the fuse melts, it'll destroy our alternator. We had a catamaran, this is like a multi-million-dollar catamaran with two engines and two big alternators, and the owner takes off on his maiden cruise from New York to go to Europe, and off the Jersey shore, he destroys both the alternators. So it's a 24-volt house system on the boat, and the alternator supplier thought maybe they'd accidentally supplied alternators with 12-volt field circuit. So they sent two new alternators, and the same installer put them in there. And then we get a phone call from the boat owner off the Jersey shore saying, my fuses are smelling. Should they be smelling? So shut that thing down. So they shut it down and they got it back in. A single stainless steel washer in the wrong place had melted the fuse the first time around, destroyed both of those alternators, and was about to do the same thing over again. So every single boat I go on with a large number of ANL and Class T fuses, I look at every single fuse on both ends of it to make sure there's no stainless steel washers in there, and you wouldn't believe the number of times I see the washers in the wrong place. So you have to be really careful about that. And I might have some slides on that, so I'm not sure that I do. Now, I mentioned the MRBF fuses earlier. These are the ones that bolt to the top of a battery post, and that's what we can see here. They're square fuses, and the battery connection is on the bottom, and the terminal is on the top going out to the conductor. And you can get these fuses rated up to maybe as much as 500 amps. However, the AIC rating on these fuses, I think, is off the top of my head, I think is 3,000 amps. So it's too low for a large lead acid battery bank, and it's way too low for a lithium ion battery bank. So these are good for smaller lead acid battery banks, but when you get into big banks, they're not appropriate, unfortunately, because otherwise they're great. The other thing we need to make sure is that all the metals in our circuits are galvanically compatible. And what you can, this is a new boat, it's only a few months old, and they've got steel nuts here holding things together, and they're already corroding. So all the bits and pieces in the system have to have to be matched up properly, galvanically and electrically. I have a large catamaran here with a pretty substantial bank of AGM batteries. And first of all, they're not strapped down. This boat has just, I think, just come across the Atlantic to the Annapolis Boat Show. Secondly, we've got these rigid connections between the batteries. So if there's any movement, it's going to stress the seals around the battery posts, and it's going to open up the seals, and that'll wreck the batteries. And then if we follow the circuits, we've got these two batteries are tied together in parallel. And these two are tied in parallel. And then we follow the conductors coming off the positive posts. We come to a big bus bar. So remember, we're allowed up to 72 inches, as close as practicable, but not to exceed 72 inches coming off the batteries. We're starting to push it here. And we've got all of these fuses. So this looks great. Now, each one of these is now a main fuse, because each one of these is connected back to the battery. So each one of these needs a high AIC rating. It's not like we put a single fuse in here, like a Class T fuse. Every one of these has to have a high AIC rating, and then each one of these is sized with a maximum amp rating based on the size of the conductor coming off it. We've also got some circuit breakers here. I don't know why they've got redundant circuit breakers. But now let's look a little bit further. So we've come off the batteries to the bus bar. Note this bus bar is not tinned. It's a copper bus bar. You should get tinned bus bars. And my favorite company for all this kind of equipment is Blue Seas. I have no commercial relationship with them, but they have excellent equipment. So we're coming along the bus bar. We've got these two conductors going off into the boat. There's not a sign of overcurrent protection anywhere. So these conductors are hardwired to the batteries with no fuses in the circuit. These are totally non-compliant from the standards perspective. And if somewhere down the line we get a short circuit between these conductors and something that's grounded, we're going to put a dead short across the batteries, and we're going to have a fire on the road. All because the fuse isn't in there. And then I've got, so now we've got, this is a fairly common scenario. Is it this one I want to look at? Yeah. We've got a bus bar here. We have a feeder conductor coming in from the battery. We have a fuse on the feeder conductor, which hopefully there's another one at the other end, the battery end, because otherwise this is totally non-standards compliant. And then we've got all of these conductors coming off the bus bar to loads. So, and then we've got this little conductor here. The ampacity of this fuse, the amp rating, is guaranteed to be higher than the ampacity of this conductor. Because if it's not, every time one of these circuits is loaded up, you're going to blow the fuse. So this conductor is not protected. The likelihood is that none of these are either, because if the ampacity of this fuse, the amp rating of this fuse, is low enough to protect these conductors individually, if all these circuits are running at the same time, the fuse is going to blow. So we probably have none of these circuits adequately overprotected, overcurrent protected. But this is, again, another new boat. And I see errors like this. Pretty much, if I do a thorough electrical inspection of any boat, new or otherwise, I can find problems with the overcurrent protection. We've got another catamaran here. We've got 6 batteries in parallel. We've gone from positive to positive to positive to positive to positive, and then negative to negative and all the way out. First of all, there's no way this strap is adequate restraint. If it gets into seriously rough weather, those batteries are going to be bouncing around all over the place. Secondly, if we look at the overcurrent protection, we've got all kinds of conductors. Whoa, thank you, Microsoft. What did it just do? Let's hope this doesn't shut everything down. Right. We've got we've got more than 4 conductors coming off the battery post, so that's another standards violation. We've got multiple conductors coming here with not a sign of a fuse anywhere. So most of those are not adequately overcurrent protected. We've got some other issues here unrelated to the overcurrent protection, which I'm going to address now so I don't forget it. When you parallel batteries, and most of us have, if we've got moderately sized boats, have more than one battery parallel together in our battery banks. If you parallel batteries in this fashion, and you take the conductors to the loads off of one end of the bank, when the boat is either charging or discharging, this battery is going to do more work than this battery. As it does more work, it will heat up. When it heats up, it gets more reactive and it does even more work. We get into a vicious circle where this battery is working really hard and this one's doing very little work. And with 6 of them like this, we are guaranteed to destroy all the batteries fairly quickly, within a year or so. So if you have parallel batteries, for years we've said, take one conductor, the negative off of one end and the positive off the other, so that you force the current through all of the batteries a bit more evenly. But nevertheless, if you look at that, you still get very uneven current distribution on charge and discharge cycles. What we need to do with these parallel installations is we need to set up a bus bar, metal bar, off the boat, and we need to come off of all of these batteries with the same length conductor. So the ones that are closest to the bus bar, you're going to have to snake the conductor around a bit because it'll be longer than it needs to be. So we have equal length conductors from every battery post to the bus bar, with a positive bus bar and a negative bus bar. And then we come off those bus bars through our main overcurrent protection device on the positive side to the boat. And that way, all of the batteries will see equal stresses in operation, and you'll greatly extend the life of the batteries. Now, if you're retrofitting a boat, it's going to take you a certain amount of work, and there'll be a bit of cost in the conductors and the bus bars and so on. But at the end of the day, the cost and the effort will be far less than the added value that you've got in terms of life expectancy for the batteries. I want to talk about something called arcing faults. So the whole overcurrent protection approach is to deal with amp flows higher than the conductor can handle. So we're dealing with basically short circuits or partial shorts that put a sudden flood of amps through the conductor and overheat it. So the fuse or circuit breaker will protect against that. We have a different kind of way of generating heat, which is if we have a loose connection. If we have a loose connection, we can get a spark. In this case, this nut wasn't done up. This is a shore power inlet on a boat. And even though there's no overcurrent situation, so a fuse or circuit breaker is not going to trip, we can still start a fire because of this loose connection, this arcing fault. And in this case, the boat burned to the waterline simply because that one nut wasn't tightened up adequately. My wife's sister-in-law's house, brand new house, burned to the ground because of a loose connection on an outlet, just a standard outlet in the wall. We had a similar situation in our own house where it almost caught fire because of a loose connection on an outlet. There is no antidote to these arcing faults other than to make sure that all your connections are done right and they're tightened up properly. So what you absolutely can't do is leave a job on a Friday afternoon half finished and come back on Monday unless you've made really good notes as to what has been done and what hasn't been done, and in particular what is tight and what is loose. One of the areas where you have a particular problem that's hard to address is with our shore power cords, because we cannot have a bolted connection at either end of the shore power cord, but by definition, because the whole purpose of the cord is to be able to plug in and unplug when you get to a dock. So we've got a pin and sleeve connection, which is an inherently weak connection, especially over time, because the friction might reduce use and we're in a salt environment, we get corrosion, and then we get a little bit of resistance because of corrosion, and then we get an arcing fault, and then we start a fire. Nowadays, especially in hot climates, we're tending to load our shore power cords pretty much up to the max with air conditioning. And those air conditioning units are running 24/7. So any weakness whatsoever in either end of the shore power cord is likely to generate an arcing fault at some point in the life of the shore cord and potentially start a fire. So you need to inspect your shore power inlets and your shore power cords. And if you see any signs of burning whatsoever, and it's generally speaking pretty obvious, you'll see little scorch marks, then you need to replace the shore power cord, or at least replace the connection, and you need to replace the inlet on your boat, because that little bit of a scorch mark is telling you the boat came very close to catching fire, and there will have been additional damage now from that arcing fault, so the boat is even more likely to catch fire. So inspect those on a regular basis. When you plug in, check the pedestal and make sure there's no signs of burn marks on the pedestal, and you'll be surprised how often you'll see scorch marks. And if there are, then really you shouldn't plug in. Of course, if you set the pedestal on fire, it's not your boat, so it's not quite such a big deal, but nevertheless, you probably shouldn't plug in.
On that note of shore power, Nigel, what is the function of a galvanic isolator?
So when you, on our boats, well, in our houses, all of our wall outlets, you've got two slotted prongs and then you've got a round one. The two slotted prongs are the hot and neutral. So they are similar to the positive and negative in a DC circuit. They're supplying the power to the circuit. But let's say we've got a piece of kit. It's a washing machine. And inside the washing machine, the hot conductor has the insulation has got worn through because of all the vibration when the washing machine's operating, and it's touching the frame of the washing machine. So now the frame of the washing machine is live. On the neutral side of our circuits, when you go to the outside of your house, you'll see there's a copper conductor going down to a metal rod that's hammered into the ground. So, and our neutral side, it's actually tied to that, and it's tied to earth ground. So let's say we've got that short to the case of the washing machine. We've just got the positive and the neutral. We got no other conductors. We go touch the washing machine. We become the path to ground because the neutral is tied back to ground, and we get electrocuted. We get a shock at least, and maybe get electrocuted. So forever, we've put a third conductor in our electrical systems, which is attached to the frame of the washing machine or everything else. And it also is tied back to ground, to earth ground. So if we get any kind of a short to the case of any electrical equipment, the path, the current flow is now through that grounding conductor back to earth ground. And if it's a serious short, it'll be enough current that'll flow to blow the breaker, trip the breaker or blow a fuse. So that's what that third conductor is doing. In our boats, that third conductor is tied to water ground. It goes back to a grounding bus, and that grounding bus at some point is tied to something that's immersed. And the water ground is our grounding system. So again, if we get some kind of a short to the case of AC equipment, it's going to run to water ground. And in the case of when we're plugged into shore power, it'll run back through the water to the dock, and it'll take care of that. And if it's a big short circuit, it'll trip the breaker in the boat or on the dock. So we've got that connection, but so has every other boat in the marina. So when we all plug in, we're all tied to the same water ground. And we're connected one boat to the other through this grounding conductor. And then we also, on our boats, typically, we have various bits of underwater metal that we put into a galvanic protection circuit. So these bits of metal are in contact with the water. We've created a circuit between them, and we've tied them back to the grounding bus as well for galvanic protection. So now we've also wired all our underwater metal. From my boat to your boat, we've wired them all together effectively through the grounding conductor. And if we've got dissimilar metals, maybe I have a bronze propeller and you have an aluminum one, my bronze is going to destroy your aluminum, or maybe you have aluminum outdrive. This is outdrives are a particular source of problem because they all have an aluminum leg on them. and aluminum is quite reactive in salt water, my bronze fittings destroy your aluminum outdrive leg. So a galvanic isolator is a piece of kit that we insert in the circuit that breaks that circuit, that galvanic circuit, without destroying the ultimate protective function of that grounding wire. And we don't need to get into how it does this, but that's what it does. So it's breaking that connection between my boat and your boat through the AC grounding wire without destroying the safety function of the grounding circuit. Now, if you get a serious AC fault on the boat that's not high enough to trip a brake runs on, you can actually override the protection of the galvanic circuit to where we're no longer isolated from other boats. So these devices should be tested once in a while and checked out, but that's a whole different subject, which it's getting a bit beyond what we can do today. I'm just looking at the time. The other way to deal with this is to put an isolation transformer on the boat, because with an isolation transformer, you bring the hot and neutral to the transformer, and then you transfer energy magnetically to the boat. There's no physical hardwired connection, and you also break the physical connection on the grounding side. So now there's no grounding circuit, there's no circuit between my boat and the dock, because we transfer the energy magnetically to the boat. So an isolation transformer is a really useful piece of kit to have on a boat. So let me interject here, because some of you probably have plans to go cruising overseas. And in the States, as you know, we have, typically speaking, we have either 120 or 240 volt electricity at 60 hertz. In Europe and most other places in the world, you're going to see 230 at 50 hertz. So you can't plug an American boat into a European or most other countries' outlets, because you'll fry the AC equipment on the boat. However, we have nowadays a lot of marine battery chargers which will accept a voltage input from 70 volts to 270 volts and a frequency of 45 to 65 hertz. So effectively, just like you can go anywhere in the world and plug in your laptop or your cell phone or your Razor, same way, these modern battery chargers, if they have this universal input capability, can be plugged in anywhere in the world. So now we can plug in our battery charger, we can charge our batteries, and if we put an inverter on the boat, not an inverter charger, so just an inverter to power the AC circuits, we can now feed the AC circuits from the battery charger to the battery to the inverter, all the AC circuits on the boat. We can plug in anywhere in the world and we can run all the AC circuits on the boat, doing it this way. And effectively, the battery charger is directly feeding current through to the inverter. And if the AC load exceeds what the battery charger is supplying, it'll suck off the batteries. And if the AC load goes below what the battery charger can supply, the battery charger will catch up and recharge the batteries. So we microcycle the batteries, but we break the physical connection between the shore power and the rest of the boat. And what's interesting in this is that all marine battery chargers are actually built around an isolation transformer. So we've effectively introduced an isolation transformer to the boat. We've disconnected the shore power from the boat's AC circuits, and we can still run all of the AC circuits, and we can plug in anywhere in the world and do this. I've been doing this on my boat for a decade or more now, and it works really well. So one other piece of kit that we have in this circuit is on the hot and neutral sides of the AC circuit. We want to see, if it's a European built boat, it'll have a piece of kit called a residual current device, an RCD. It's a little box with a breaker on it, typically with a breaker. They don't necessarily have a breaker built in, but they mostly do. In the States, we have a similar device, except we call it an electric leakage circuit interrupter, an ELC, but it basically serves the same function. What these devices do is if we have any, let's say we do have that short to the case of a piece of equipment, but it's a minor short, so it's not actually causing any problems with the equipment and is not tripping the circuit breaker, but it could still be potentially lethal if it gets into the water. If that RCD or ELCI sees a leakage current of more than 5 thousandths of an amp, so I mean, sorry, 30 thousandths of an amp, so it's a tiny leakage current, 30 thousandths of an amp, it will trip and shut the circuit down. So it's a really important safety device. The Europeans have been fitting these for decades. So if you have a European built boat, it's almost guaranteed to have one. We only started requiring these in the States with new builds starting in 2013, 10 years ago. So if you have an older American built boat or from some other countries, it probably does not have an RCD or ELCI. And if you plug in on a regular basis, you should fit one. And again, Blue Sea is a good source for this because it's a really critical piece of safety. And especially if you're boating in fresh water, because the risk of electrocuting people from low-level leaks on the boat is much higher in fresh water than it is in salt water. So if you do any boating in fresh water, you absolutely should have a RCD or ELCI on the AC input to the boat, regardless of whether you've just got that one battery charger or whether you've got an entire AC system that's powered from the dock. Well, that was a bit of a digression. So coming back to batteries for a moment, how big a battery bank do we need on a boat? Well, all of you need to do an exercise to calculate what your loads are and figure out how much energy you're actually using. The way we typically do this is to list all the loads on the boat. We figure out what their amp draw is. We look at the label or we go to the literature or whatever. We multiply, we figure out how many hours a day they're running, and much of this is guesswork. For example, if it's a fridge, which is cycling on and off for over 24 hours, it might be on for 8 hours or it might be on for 12. So we make some educated guesses and we multiply the amp draw by the time, and it gives us a number called amp hours. It tells us how much energy we're using with that particular device over 24 hours. And we do that for all the devices on the boat. We do a similar calculation for any devices that we're running off an inverter, because the inverter is a DC load. It's sucking off the batteries to power the AC equipment. And we get a total load number that's coming off the batteries. And if we say recharge twice a day because we're on a power boat where we run a generator to cook morning and evening, then we're going to cut that 24-hour load in half because we're recharging twice a day. If we're on a sailboat where we want to sit on the hook for 4 days without running a charging device, we're going to multiply it by 4. But one way or another, we're going to come up with a number that tells us how much energy we're using in between opportunities to recharge the batteries. And that's a really important number for any boat. If you go to the Ocean Planet Energy website, Ocean Planet Energy, all the words run together, oceanplanetenergy.com, they have a calculator that you can download to do this, where you just plug in all the numbers and then it'll sum them for you and so on. So we come up with this load number. We also, if we've got lithium-ion batteries on the boat, we want to know what the peak instantaneous load might be. Let's say we have a bow thruster and a windlass, and for some reason we run them both at the same time. That's likely to be the peak instantaneous load on the boat, and it could be hundreds of amps. My bow thruster pulled 700 amps. The battery management system, the piece of electronics that creates the safety for a lithium-ion battery, has got inside of it a disconnect. And if it sees a current above an amp, above a certain level, it's going to disconnect the battery. So what we discovered, and also the same goes for cranking currents. When we start putting lithium-ion batteries on these short-term high current loads like bow thrusters and windlasses and cranking motors, we often find that the current draw exceeds the amp limit in the BMS, at which point the BMS disconnects the battery from the boat. And if, for example, we've got the engine running, because we're using the bow thruster and the windlass, we're leaving an anchorage, and the battery disconnects, and we have no other alternative backup, and we've got a big alternator that we just put on there that cost us a fortune, and it's wired to the lithium-ion battery that has just disconnected. We've just destroyed the alternator. Before the alternator fails, it will have put a massive voltage spike through the boat, and we may have blown every piece of electronic equipment that happens to be turned on at that time, which is all our navigational equipment. And again, we've had instances of this where in a moment, because of some high inrush current to some device, the batteries have disconnected. There's been no backup in the system. It's a fairly large trawler yacht. You've just blown $100,000 worth of electronics on the boat. So we need that number for lithium-ion batteries. We need the worst case instantaneous load on the battery, and we need to make sure that we cannot exceed it, or if we can, that we have backups in the system. So now we have a load number, an energy requirement number for the day or however long we're going to run this. And then if we're using wet cell lead acid batteries, that's the type you top up, the battery capacity needs to be 3 to 4 times that load number we've come up with. It's a huge amount of lead that we end up putting in the boat. If we don't do that, we end up deeply discharging the batteries on a regular basis, and we end up killing the batteries. If we go to high-end AGM batteries, like the Lifelines, we can probably squeeze that down to 2 to 1. So the battery capacity needs to be double the load number. But we're really kind of pushing things a little bit there. Within the AGM world, we've got 2 technologies that have come out in the past decade. One is thin plate pure lead. These are batteries from North Star and Enesys Odyssey batteries. These have higher discharge and recharge rates than regular lead acid batteries, and which enables you to push the battery a little harder. So then we can get away with the 2 to 1 ratio. And then we have a battery from a company called Firefly, which is unique in as much as inside the battery it has carbon foam negative plates, which we won't get into what that does, but it totally changes the way those batteries react to deep discharges and so on. You can definitely put the 2 to 1 ratio onto the Firefly batteries, but I need to caution you, the quality control with those batteries was pretty awful during COVID, and I don't know that it's recovered. They're expensive. I wouldn't recommend them until they got a better track record than they have right now. The technology is terrific.
Yeah, we've had some negative results from South Pacific Posse participants in the South Pacific where they're like, they died basically.
Yep, it's a terrific. I had some good ones that I just beat the crap out of for years to see if they could take it, and they absolutely could. And they've got other properties which are really useful. I'm hoping the core problem there is that Firefly has a patent that stops other people from producing similar batteries. But there are competing technologies coming out of New Zealand that hopefully they'll be able to ineffectively create a similar battery without voiding the patent, and with a much higher quality control processes, and then that would be really good. So then when we get to lithium ion, people will tell you that you can use 100% of a lithium ion battery's capacity. That's nonsense. You never want to run a lithium ion battery totally dead. You always want to have a buffer of at least 10% on the bottom end, just to be a little cautious, because there are certain conditions when lithium-ion batteries are totally dead, especially if they're left totally dead, where when you try to recharge them, they can go into thermal runaway and catch fire. And on the recharge cycle, it's often practical to not run all the way up, to maybe stop at 80 or 90% state of charge. For various reasons. So my generic formula for lithium ion is assume that on a regular basis, you're going to use 70% of the capacity, which means that the battery bank needs to be 1.4 times the energy, the capacity of the battery bank, 1.4 times the energy you're going to take out of it. Even so, that's less than half the ratio for wet cell batteries. So half as many batteries, half as much capacity is going to do the same amount of work. And in practice, it's going to do a lot more work because the lithium ion are much more efficient and perform better and so on. And plus the lithium ion will be a quarter the weight of the lead acid and less volume and so on. So lots of reasons to go to lithium ion. It's a terrific technology. But on that, you should not, you can go online and you can buy cells and you can buy battery management systems and you can package them up yourself, and you can create a battery that has cost you maybe $200 or $300 a kilowatt hour of capacity. Whereas when you go looking at retail prices for marine companies selling lithium ion batteries, you're typically looking at $800 to $1,000 a kilowatt hour. I absolutely would not do that. There are so many different ways in which lithium ion batteries can, if abused or not properly installed, get into thermal runaway, which is a condition where they go into internal heating, and even though you turn them off or disconnect them, it doesn't stop. It's self-reinforcing, and then they can get hot enough. Even lithium iron phosphate, which is theoretically will not generate high enough temperatures to set itself on fire, they can all still catch fire because the electrolyte is flammable. And when they start to go into thermal runaway, the pressure builds up inside them, the plates short out, there's arcing. The arcing sets the electrolyte on fire. It doesn't matter if it's lithium iron phosphate or nickel manganese cobalt. At some point, all of these batteries can catch fire. And when they catch fire, they're very hard to put out. And the basic result is you lose the boat. So I love lithium ion. I've had it on the boat for years. But my two parameters for lithium ion are either the battery needs to have been tested and listed. So some battery manufacturers will say they test to a certain standard, but if it's not listed, it doesn't mean it was tested by the people that wrote the standard. So you want it tested and listed to UL 1973, which is by far the most aggressive testing standard in the marine marketplace. If you've got a UL 1973 listed battery, it's pretty much impossible, regardless of what kind of mistakes you make or installation errors, pretty much impossible to get that battery to go into thermal runaway, and virtually impossible to set it on fire. But if it's not UL 1973 listed, which at the moment, the only ones that I know are listed are some of the Lithionics batteries, not all of them. If it's not UL 1973 listed, I want it to come from a company that's been around for years in the boat world and has a really high reputation. Somebody like Torqeedo or Masterbolt or Victron. I'm not going to go for a battery that's new to the market and somebody that's trying to break into the boat world until a few thousand units have been out there on other people's boats, and that we know that from anecdotal evidence that those batteries are safe.
And we also know that now there's new insurance requirements coming with regards to lithium ion banks, including, you know, as much as many of us struggling getting insurance because we are in the tropics, we're already there. New requirements coming down are becoming even harsher when it comes to those installations, including that the installer has to be a certified installer, etc.
So thank you. My insurance used to be with Markle, the jackline policy, which I think a number of you have. They yanked my policy last year because of the lithium ion batteries I have on the boat. They have a policy now, any boat with a valuation of more than $150,000, they will not insure it with lithium ion batteries.
Correct.
My batteries came from Torqeedo. You know, there's a really high-end provider. They're professionally installed. They've got multiple layers of safety built into them. And nothing I could do would persuade Markle to reinstate that policy. And I had a hell of a time finding another company that would insure the boat. Yeah,
and as I said, and that's Nigel not getting insured, right?
Yeah. So, and I am through the ABYC, I'm trying to get together some activity where we can go to the insurance companies and get our heads around this, because this is a knee-jerk reaction on the part of the insurance company to some poor installations that have set boats on fire. It's not, I'm sure their data doesn't really support this. The problem they have is that if a boat does catch fire, it's a big claim. And if the boat's in a marina, it also sets the marina on fire, and it maybe sets the neighboring boats on fire, and they end up with the massive claim. In actual fact, a bigger risk on these boats, especially when we get to large yachts, is all the toys on board. You know, I was on a super yacht the other day that has a submarine with lithium-ion batteries. It has a PWC, a personal watercraft with lithium-ion batteries. It has dive lights with lithium-ion batteries. I mean, there's no regulation on how these get installed on boats or managed or charged, or whether they need to be in a locker where they won't get flooded. So a lot of the things we bring on board the boat are actually a bigger risk these days than a well-installed lithium-ion battery bank.
Yeah, copy that.
The insurers are going to take a while to catch up.
Yeah, thank you. Thanks for addressing that, and we are fully aware of that.
Yep. So let's talk just a little bit about monitoring. Most of us have got relatively high house loads. We're trying to charge batteries fairly quickly so that we don't have to run engines and generators for hours a day. We're pushing our systems fairly hard, which is why it's so important to size the conductors properly, to put the terminals on properly, to make sure you got overcurrent protection and we have no arcing faults and so on. But we still need to know what's going on inside the system. So we need accurate monitoring. Fundamentally, we need to be able to measure voltage at the batteries and not somewhere else in the system, because voltage drop might give us an inaccurate reading. And we need to probably know what the current flows are in and out of the batteries, so that then we can monitor state of charge of the batteries. So those are the two key things we need to know, is voltage and state of charge. And if we can measure voltage, then we can also make sure that the various parameters we've got when we're charging, the absorption charge, which is the one that we maintain for a considerable length of time until the battery is almost fully charged. We need to know that the voltage on that is within a tenth or two of being exactly where it should be. And then when our batteries get to be fully charged, typically speaking, our charging device is tripped to a float setting. We need to be able to check the float setting to make sure that as well is within a tenth or two of a volt of what the battery manufacturer wants to see, because if it's out more than that, it's also going to damage the batteries. So we need to be able to measure the absorption and the float voltages at the batteries. We need to do this for every charging device on the boat individually, so that we make sure that none of those charging devices are potentially wrecking our batteries. So we test it with the alternators, with the battery chargers, with the solar array, or whatever, and make sure that those two voltages are within spec for all the different charging devices. And then, of course, we need that some kind of a way of measuring amps so that we can track the state of charge. What we haven't ever been able to do with our batteries is measure the state of health of the batteries. So as they age over time, we've not really been able to measure that. We do have coming on the market now some devices which claim to measure state of health. I don't know how reliable they're going to be. I think Balmar has one. So it'll be interesting to see how that plays out in the lead acid world. In the automotive world, the various standards in the auto world now do require that they measure state of health. So I think that technology will spill over into lithium-ion battery installations on boats over the next few years. So I've got about 10 minutes left. I want to talk a little bit about troubleshooting. I think at this point might be the most useful thing I can do with the remaining time. And let's see if I can find that little module. These, incidentally, are all of the different courses we have on our boat how-to site. We have a basic electricals 101, which covers all of the kind of things we've just been talking about. and in great detail with lots of videos and illustrations. And then we have an advanced course where we get into AC systems, some of those questions that just came up, corrosion, lightning protection, power generation, and all the way up to hybrid systems and so on. So 2 separate courses. We're working on a diesel maintenance course right now, which hopefully will be out maybe the middle of next year. And maybe an electronics one after that, but that won't be before the end of next year. So let's look a little bit at troubleshooting. First thing you need is a decent meter. And I'm not sure if I have any slides on meters. No, so not easily accessible. They're buried in there. You want to be able to measure voltage, AC and DC. And that actually, for simple troubleshooting, is all you need. When we get into other measurement modes, such as resistance, ohms, and even amps, some meters you can measure amps through the meter up to 10 amps. You can potentially get into trouble if you're not used to using a meter. So I tell people, absolutely, if you're a novice with a meter, just stick in the volts mode and make sure you've got AC and DC volts, and ideally have separate switch positions for that. Because if a lot of meters have a common switch position and then you have to toggle between AC and DC, and you've got a tiny little LCD screen and an even tinier little DC and AC symbol, and it's very easy to be in the wrong mode and not realize it. So we want to be able to measure that. But something that's really useful is a DC amps clamp. I've got actually a bunch of meters here. Come to think of it. Let's see. That's a clamp meter. Here's a meter which will measure. It's got volts, separate switch positions, AC and DC, which is terrific. We got some other stuff here. We can measure resistance, and we can measure amps up to 10 amps by moving the meter leads. So, and then what we have to do is open the circuit, cut the circuit, and insert the meter in the circuit. So the amps are running through the meter. Well, I did this one time with one of these meters, a cheap one that had just been sent to me through the mail, and I was testing it. And I forgot to reposition the meter probes after doing this. And I went and did a test across the house outlet. And there was a big bang and a cloud of smoke, and the meter leads vaporized. I mean, literally, and I'm left holding the 2 plastic leads. And then nothing else, because I had put a dead short across the house because I'd forgotten to reposition the meter leads, and this cheap meter didn't have any internal protection against somebody making that kind of mistake. So the bottom line is, the more you pay for a meter, the more safety features it'll have, and also higher levels of accuracy and so on. So don't go buying some dipshit meter for $10. Get a decent meter and pay some money for it. And then if you want the amp clamp, which is a way of measuring amps safely as opposed to feeding them through the meter. Basically, you clamp that around the conductor and it measures amps. And there's no way you can get into trouble doing that. So that's a terrific piece of kit. The vast majority of amp clamps on the market only measure AC amps. So you want one that measures DC amps. This is a meter from Craftsman Sears that I got many years ago. Was like $60. It's got all of these features, but I had to buy 2 to get one that worked. If we go a step up to 100 plus, we're pretty much guaranteed it's going to work out of the box. The other piece of kit that I highly recommend you get for novice troubleshooters is a meter lead extension kit. You can, this is up to 30 feet. You can pull it out, and and I'll explain why that's such a useful piece of kit. And now we're going to stick in the volts mode, because that way it's almost impossible to hurt yourself, the boat, or the meter in the volts mode, as long as you don't poke the probes into moving parts and you don't touch any live AC terminals. So obviously the first thing we do before we go poking around in the boat's wiring is we shut down all the AC circuits, we disconnect the shore power cord, we turn off any generator, we make sure the inverter is turned off so that we don't accidentally energize that. So if we think of a circuit, we've got a battery, we've got the main fuse that I talked about with the right AIC rating, we've got a switch, we've got some kind of other switch in the circuit, we'll get to what this is in a minute. Then we've got a device, in this case we're looking at a motor, and then we go back to battery negative. When we close all of these switches to power up the motor, what we've done with the wiring and all the other bits and pieces in the boat is we've effectively moved the battery to the motor. I mean, that's the function of the circuit, is to get the energy that's stored in the battery and to supply it to the motor. So in theory, if we have a perfect circuit, if we test across the battery posts to see what the voltage is, the battery voltage, basically we've moved the battery to the load. We should also measure battery voltage across the load. In fact, we're going to read a little below battery voltage because the voltage drop in the circuit. But it's going to be close, within 10%, as long as the circuit has been properly established. So again, if we think about, we've got all the switches closed. What we've done on this side of the circuit, we've effectively moved the battery post up to here, the positive post. On this side of the circuit, we've moved the negative post to here. And that's a function of the wiring. It's basically to move the battery posts up to the load. Well, now, let's open this switch, but this one, we'll keep this one closed. So we've now moved the positive battery post as far as here, and here it stopped because the switch is open. The negative, we've moved the negative battery post up to the load, and here's the bit that I know a lot of you have trouble with. Most of the loads on our boat, when they're not turned on, remember we've got the switch open, look like a piece of wire to a meter in its volts mode. So at this point, we've now moved the negative battery post through the load, whatever it happens to be, to here. So we've got positive here and negative here, and if we put the voltmeter across the open switch, we should read battery voltage. That's assuming this switch is closed, so this is the only break in the circuit. And if you can get this concept through your heads, that what we're doing with the wiring and the switches and things in our boat is just moving the battery posts around the boat. And think about, in a given situation with switches and fuses in certain applications, where are the battery posts right now? And where am I going to read battery voltage? So when we're troubleshooting, we're looking for voltage where it should be, voltage where we're not expecting it, and less voltage than we're expecting. So we're looking for voltage anomalies. And in order to understand the voltage readings we're getting, we need to have this picture in our heads. And actually, we should sketch it down on paper of what's going on in the circuits. So in a windlass circuit, I have a bad habit of running aground. That's one of my groundings. And then I've used the windlass to drag myself off, and I've fried 4 windlasses over the years. So in a windlass circuit, you've got the big high current circuit to the windlass, which is going through an isolation switch, and then a solenoid switch. A solenoid is just a remotely operated switch. And then the windlass motor, and then back to battery negative. And then the control circuit, the one that's triggering the windlass, again, it may or may not have a switch in it. And then in our case, we have foot switches on the boat. Some of you have buttons in a remote. But anyway, there's a switch. When you energize this switch, you're actually energizing a magnet in the solenoid, and the magnet is driving a plunger, which is closing the solenoid and making the circuit. So that's what the foot switch circuit is doing. But basically, we have 2 circuits, each of which has the same property. They start at a battery, they go through a variety of switches and fuses, they come to a load, and they go back to battery negative. So in essence, they're the same. What differs is the bits and pieces in the circuit and the size of the conductors and so on. So my windlass just failed, and my foot switches are installed in over a locker in which I keep my spinnaker. So when I got a problem, I go for the accessible places first, not necessarily the ones where I think the problem is, but just to collect data. So I turn on the various circuits, and I go to the locker, and I drag the sail out, and I get in the locker, and I put my meter probes across the switch terminals on the underside of the switch here. At this point, the switch is open, it's not in use, but everything else on the circuit is turned on. So what I should see is battery voltage, because I've effectively moved the two battery terminals up to the switch. When Terry, my wife, steps on the switch, that battery voltage should go to 0 volts, because at that point, the switch looks like a piece of wire to the meter. And even though my 2 meter probes are on either side of the switch, they might just as well be on the same terminal, because we've just closed the switch and it's just a single piece of wire. But in fact, when Terry steps on the switch, I've still got 25.62 volts battery voltage. That tells me, even though she's standing on the switch is still open. Right there, it took me, the most difficult part of this job was pulling the sail out of the sail locker. And because I knew what voltages I should be seeing, and I didn't get those voltages, I knew the switch had failed. So indeed, in all of these switches, you've got a plate and there's a spring. And when you stand on the switch, you push the plate down against the spring and it hits the 2 terminals in the switch. And every time you do that with a high current circuit like a windlass, there's a little spark when you make the circuit and when you break the circuit, and it burns the plate. And all I had to do in this case was to clean it up with a file and wet and dry sandpaper and put it back together again, and it worked fine. So now it's okay to run over a little, Dieter. So here I am.
Absolutely.
Underneath there, across the switch. Switch is open. I got 25.1 volts. Mine's a 24-volt boat. And when the windlass has failed again, and when Terry steps on the switch, it goes to 0 volts. So now I know the switch is working. Same thing with the up and down, both switches. I get the same result. So I know both switches are working. So the problem is not in the control circuit. So now I need to either access the solenoid pack, which is the 2 solenoids that do the up and down for the windlass, or the motor on the windlass. Well, in fact, it's easier to get to the motor on the windlass. And my particular windlass has a positive and a negative terminal on the motor, and it's got what's called reversing solenoid. So when we go on one switch, we get positive to negative, and when we hit the other switch, we get negative to positive. So we reverse the polarity in the circuit. Some of you have 3 wires on your windlass motors, and one of which is the negative, and one's the up positive, and the other's a down positive. So there's different arrangements for doing this. But anyway, I go to my windlass motor, and I get the 2 terminals in my case, and I put the meter on them, and I get Terry to stand on the up switch and the down switch, and I get plus 25 volts with one switch and minus with the other. So I know the solenoid packs are working. I got voltage at the motor. I know the motor's failed. And indeed, on this particular occasion, I had run the boat aground. Actually, we fouled a big mooring chain in France. And in getting ourselves free, we had overloaded the windlass. And it got hot enough to where inside the windlass is this commutator. And these pieces are glued in place. The commutator segment came unglued and flew out and destroyed the motor. So I had to get a new motor. So then I get, the next year, I get another windlass failure, except it's turning very slowly, but not very well at all. And I go through the same exercise. The up and down switches are working fine. I don't have any slides for that. They're in another presentation somewhere. So the up and down circuits are working fine. I go to the motor. I'm getting plus or minus 25 volts at the motor. I get my current clamp out, and I clamp the conductors, and I'm pulling 30 amps where I should be pulling well over 100. So there's something going on inside the motor. It's a brand new motor because it's the one I had to buy to replace the one I fried the year before. So I pull the motor out and take it apart. And in this case, that new motor, inside of these motors, you have carbon brushes with springs behind them. One of the brushes was split from manufacturing and hanging up in the brush holder, and so only half the circuit was getting energized. So it was a manufacturing defect. So the bottom line here is I was getting the voltages I expected, but I wasn't getting the amps that I knew I should be getting. So once again, I knew the trouble was in the motor. So if you know what you should get, and you get an anomaly, then something's going on right there. So now the long meter lead. Let's just cover this, and then we'll call it quits for the day. Let's say we have a circuit, and we'll take the window circuit again. It's acting up, and we're really having trouble figuring out what's going on. If we, let me back up. Where's that window circuit? Okay, let's just take a simple circuit. If we take our long meter lead and we clip it, say, to battery negative, right here. Let's assume this switch is closed, and this one is open. This is the foot switch. So we've powered up the foot switch circuit, but the foot switch is not in operation. We're on battery negative, so negative goes all the way here, and then we get our meter lead attached to the other end of this long meter lead, and we go here. We should read battery voltage because we've got positive to here, and we've got negative to here. And we've taken our long meter lead from negative to positive. We should read battery voltage. Let's say we don't. So we go back, we find a connection in the circuit somewhere back here. We touch that, we're still not getting battery voltage. We come back, we're still not getting battery voltage. We come back, all of a sudden we're getting battery voltage. Between the last place we took a reading and this place, we know there's a break in the circuit. In this case, there was a switch that was open that we thought was closed. So with this long meter lead and a voltmeter, you can work your way through an entire circuit and taking readings. And at some point, there will be a substantial change in the voltage readings. And in between the last point and this point, there's something going on in the circuit.
And what length should they? What
well,
length
this is
works for 40-foot?
Pretty standard thing at 30 feet.
Okay.
Which,
Great.
you know, for some boats is probably a little on the short side, but for most of our boats, because the batteries are typically not all the way to the back of the boat, you can get, and then we can do the same thing on the other side of the switch. We can clip on to battery positive, and then if we go to the negative side, we should read battery negative, and if we don't, I mean, we should read battery voltage rather, and then we start working our way back through the circuit, and all of a sudden we get battery voltage, and we know between that place and this place, there's a break in the circuit. It's a really, really quick and easy way to isolate the location of faults. What is even better is if we can power up a circuit. If we've got an underperforming circuit, and then if let's say we have 12.6 volts at the battery, and at the windlass we're reading 9 volts. So we're dropping 3.6 volts in the circuit, 20+% voltage drop. So if we do the same thing, we hook onto battery negative and we go to the positive terminal. So when we need our long meter lead, we're going to read battery voltage. Sorry, let me change this. We put the meter lead in this case. This is a circuit that we can energize, but it's not performing properly. So we can load it up. We put the meter lead on battery positive. We go to the positive terminal on the device. We've established that we're losing 3.6 volts. We took a reading across the battery and then we took a reading at the load. So we go from here to here and we measure the voltage. Now, in a perfect world, this is a single piece of wire with all the switches and fuses closed. In a perfect world, we'd read 0 volts because it's just like we put the 2 meter probes on the same battery post. So whatever we read here, maybe we read 3 volts, is voltage drop in that side of the circuit. And then we can do the same thing. We can start working our way back, taking readings. If we get a uniform reduction in voltage readings as we go back along the length of this conductor and through all the bits and pieces of kit, then the conductor is undersized. It's causing the voltage drop. If, however, we get a sudden change in the voltage drop, sudden reduction, between the last place we were at and the next one, we've got some resistance. It's probably bad connections in the circuit, corroded terminals or whatever. And that way we can trace those parts of a circuit that are creating unwanted resistance and sort them out. But this test only works if you can load the circuit. It's like a stress test for a bank. The circuit's got to be loaded in order to create the voltage drop so that we can then track down where the voltage drop is. And once again, we're using the voltmeter, so it's pretty well impossible to hurt ourselves or the boat or the meter, as long as we don't poke the probes into moving parts and touch live AC terminals. And we can go through the boat and figure out where we've got poor terminals and corrosion and so on. A circuit which is really good to do this on a preliminary test is your cranking circuit, because typically the battery is close to the starter motor, so it's easy to do it. If you put the meter in volts mode again, DC volts, 1 probe on the battery positive post, and then if you have a solenoid, an older boat with 2 big terminals on it, one has the battery cable coming in, the other has a strap going down into the starter motor. If you put your meter probe on that second solenoid terminal, so the one that's going down into the starter motor, so we're on battery positive to solenoid output terminal, and you have somebody crank the engine, you'll be reading the voltage drop on the positive side of the cranking circuit. And it's not uncommon to see 2 and 3 and 4 volts, in which case you need to find out where the resistance is. So now, if we have a battery isolation switch, we can go across the 2 meter probe and the 2 switch terminals with the switch closed and have somebody crank. And what we'll be reading is the voltage drop through the switch when we're cranking. And if the switch points are burned or corroded, we'll get maybe a half a volt or a volt. So we know we need to replace the switch. Much more likely is if we go to the solenoid, the 2 terminals, the big terminals on the solenoid, we put the meter probes across those 2 big terminals, and we have somebody crank, we're much more likely to find that's where most of the voltage drop is, because inside that solenoid, exactly the same as with our windlass foot switch, there's a plate that gets thrown out by a magnet, and every time it engages, it arcs and it burns it until it starts to make a bad connection. And having discovered that it's the solenoid that's the problem, if it's an older boat with the 2 terminals, on the newer boats, that second terminal is buried inside the starter motor. If you've got those 2 terminals, you can actually pull the solenoid off and take it apart, take that plate out, just the same as with my windlass, clean it up, put it back together again, and it'll work just fine. And you just saved yourselves the cost of a new starter motor. So there's really a very limited look at troubleshooting, but the voltmeter with the extension lead, a sketch of the circuit, and an understanding of where conceptually the battery posts are in the system with a given set of circumstances. You put those 3 things together and you will be able to identify the location of most electrical problems on a boat fairly quickly. Just last week, my daughter's neighbor's house burned down in New Orleans, and they called me down there to take a look. I suspected it was an electrical fault. So I got my long meter lead and I connected it to the panel, and then I went around the house, checking what wires were connected where, looking for, in this case, I was using the resistance function, but looking to see where I had connections through the house, and I was able to identify the cause of the fire and where it started through basically the same set of tests, but using an ohm meter, which we won't get into now because we're out of time.
Nigel, thank you.
Yeah.
Thank you so much. And I can only tell you that I have been taking the tests, and it's a lot to absorb. I feel like I'm back to school, but it's a really good site for you to wrap your head around. I'm gonna just ask if anybody's got any questions. Please unmute your mics and go ahead. Ask Nigel any questions that you may have. And if not, we're going to close it for today. And everybody, thank you for being part of this.
Nigel, can I ask a question of you? It's kind of complicated, but hopefully you can straighten it out for me.
Mm-hmm.
I'm having my boat rewired because electrician looked down there and said, man, this is a mess. Anyhow, so right now what I have on the boat, it's a 46-foot motor yacht, best way. It's a 50 amp, 125 volt. Now, there's been some question. The electrician was talking about taking it down to a 30 amp because it's easier to connect through the marinas.
Yep.
That to me was intuitively wrong. You would think I'd want more power, less power. And then there's a question between the 50 amp 125 and the 50 amp 125 240.
Yeah.
Can you I am just completely confused with all this. He says, I've got a 50 amp 125. He said, that's perfect because right now I have it hooked up to 230 amps wide into my power that comes into the boat. And he says that's dual phase and that's what you want. All this is very confusing to me. Can you kind of straighten this out? What do I want to put in my boat to go down Central America? And Dimar, maybe you can help a little bit here too, as to talk about the availability in marinas down through there. What do they use?
I'll let Nigel speak to his, and then we can talk on another time about what's available.
Okay, sounds good.
The bottom line is I can't really deal with this in this environment. It's too big a question.
I kind of figured.
But if your aggregate loads can be handled with the 30 amp shore power cord, and everything on the boat is you don't have any 240 volt equipment. So let me back up a moment. If you go to the panel board in any American house and open it up, you'll see that we have 220 volt legs coming in. And most of our equipment, standard household outlets and so on, are wired to one or other of those legs at 120 volts. And then for 240 volt equipment, like clothes dryers and the ranges, electric ranges and big air conditioning units, they've wired across the 220 volt legs to get 240 volts. Well, it doesn't sound to me like you have any 240 volt loads on the boat, in which case the only question is as to whether a 30 amp cord would be able to handle the loads. And if so, I agree with your electrician, you'll have far more choice in terms of being able to plug in. And not only that, the 30 amp cord will be a third of the price of the 50 amp and much easier to handle. However, if your loads are such that you would be running that 30 amp cord close to its 30 amp rating for extended periods of time, then you're getting to that point where you're stressing the connections at both ends. You're possibly going to get arcing faults at some point in the future if there's any corrosion. It would be much better to stay on the conservative side and go to a 50 amp cord or two cords. As regards how to wire this on the boat, I can't get into that right now.
Yeah, and Curtis, one other thing is, if you're up in San Francisco right now where the weather is nice and cool, that may be a good option. But once you get into the tropics and you want to run your air conditioning system, you're going to want that second circuit and you're going to want to run AC. And that's where the dual circuit comes in handy.
Ah, excellent. Okay, that actually helps.
Yeah, I figured that much. anyhow, but you and we can talk about that, Curtis, offline. Nigel, what else do you have for us? Any last words of wisdoms or any questions by anybody out there?
Be conservative with the
Yes.
with all the wiring and the connections, and make sure that anybody that's doing electrical work, including yourself, really does know what they're doing and understands the standards. And if you have any nagging doubts about your own ability, you should not be doing it. You need to have a little modesty here in terms of your own capabilities, because an awful lot of electrical problems on our boats are self-induced by the owners.
I've got a question. My name is Mark. Nigel,
Go ahead,
thanks.
Mark.
Thanks, Dietmar. This was super and really terrific. And what it illustrated to me is the degree to which I thought I was competent enough to do work on my own boat, and I have dabbled in it. And now I have to go back and revisit everything. So it was a holy shit moment. And I'd love to investigate taking your course. And I'm wondering, this is a question for both of you, Dietmar and Nigel, whether or not there's a Panama Posse discount on the courses offered, just to be opportunistic.
Yes, of course there is. And Nigel has been very kind to us, and we obviously promote Nigel because one, he's the granddaddy of it all, and we really appreciate it. So yes, there is a code, and I'll send you that out in an email. Just send us an email and we'll respond with a code.
Copy that. I will absolutely do that. This is super invaluable, and I can't wait for the diesel mechanics courses to be offered next year as well. I will take those as well.
All right, Nigel, thank you so much for your time. As always, I appreciate it. Have a great fall, and hopefully I'll get to see you at the Annapolis Boat Show. Step by. We'll have a bottle of rum for you stashed away.
Well, thank you.
All right, guys. Thank you, everybody. We will save that and make that available to the posse online as well. Thank you, Nigel, and have a great day, everybody. Have a great weekend. Thank you very much.
Thank you.
Thanks, everybody.
Thank you.
Thank you.